So last time at the end of class, we started on the subject of what was the Babylonian value for pi? Well, in most calculations, so based on looking at how they calculated certain things, it looked like it was pretty common for them to use 3 as their value of pi. But we need to understand what we mean by that. And so this again is just a review of what we did at the end of class last time. So there are 2 different interpretations of what does pi mean. Now, first of all, just keep in mind that the Babylonians didn't have a symbol for pi. They didn't have the concept of pi like we do, but rather, what number did they use when they were calculating ratios? So one interpretation of pi is what I'm referring to as circumference pi. So meaning, if you used the formula that the circumference of a circle is some number that we call pi times the diameter, if we solve for this number, we get that it's the ratio of the circumference divided by the diameter. So that's one interpretation of when we say pi, what do we mean? We mean the ratio of the circumference to the diameter. But there's another formula where the number pi pops up, and that is the area of a circle. Now, the area of the circle is some number that we call pi times the radius squared. So what is this number? Well, let's just solve for that number. And that's going to be the area divided by the radius squared. So this is what I'm referring to as the area pi. So the pi that you get by taking a ratio of the area to the square of the radius. Now we saw that the Egyptians in the Rhind papyrus, problem number 50. So that was something where they took a circle and then they put it into a 9 by 9 square and then basically counted squares to figure out what the area of the circle would be. And then looking at that calculation, we concluded that the value that they would have used for pi is about 3.16. But even the Egyptians, when they were talking about circumference, they didn't know that the number that you have in this formula is the same as the number that you use here. And so even the Egyptians often used 3 when they were looking at the ratio of the circumference to the diameter. It was only much later, so remember the time period that we're looking at for the Babylonians is, let's say roughly 1600 BCE, thereabouts. And so it was more than 1,000 years later that Archimedes proved that, you know what, those 2 numbers are the same. Okay, so I see a question in the chat. So do we assume that they knew that the product of reciprocals is equal to 1? So yes, but And in fact, we're going to see an example of that with Babylonian fractions. However, even though I'm using algebraic notation to explain this, I want to be clear that neither the Egyptians nor the Babylonians had anything remotely like an algebraic notation. So basically, they used words to describe what steps they were doing. So yes, they knew about reciprocals. They knew that multiplying reciprocals gave you 1. Okay, so that was a great question. Thank you. So now let's look at what's on the Susa tablet. Okay, and I see a question about attendance. Yeah, so if you arrived recently, just type your name in the chat. Okay. So in trying to understand what's on this tablet, it appears as though they actually realized that 3 was not the best value for the ratio of the circumference to the diameter. And in fact, it appears as though they have a better value in this tablet. So we're going to take a look at that. Now, in that tablet, we see several constants, but one of them is this constant. So remember, we're working in base 60, and so they used so-called digits of 1 to 59. So 57 is a base 60 digit, and 36 is another base 60 digit. Now, the wording on this tablet appears to suggest that it has to do with comparing the circumference of a circle to the perimeter of a hexagon where they both have the same diameter. So here's the hexagon inscribed in a circle, and they both have the same diameter. So the scholars are suggesting that this number right here is the following ratio. If you take the perimeter of the hexagon divided by the circumference of the circle, you get a number that's slightly less than 1. So the integer part of the number is 0. And then the fractional part contains the base 60 digits, 57 and 36. So if you look at this picture, it does appear that the perimeter of the hexagon is smaller than the circumference of the circle. So for the circumference of the circle is going to be pi times the diameter of the circle. Whereas if you calculate the perimeter of the corresponding hexagon, that's inscribed in the circle. So inscribed means that the corners of the hexagon just touch the circle all around. So if going from here to here is the diameter of the circle, then halfway is the radius of the circle. So that's why I use the letter R, because it's the same as the radius of the circle. Now the question is, what is the perimeter of this hexagon? Well, here's a trick. let's figure out what kind of triangles these are. Well, first of all, if you look at one triangle, it's clear that two legs are exactly the same. We don't know yet how big this leg is, but these two are exactly the same. So that means that the base angles are going to be congruent. But then what's the angle in the center? Well, if you go all the way around the circle, that's 360 degrees. And then you divide it evenly into 6, that leaves us with this angle being 60 degrees. And then these two angles are the same. So you take and remember that the angles in a triangle add up to 180. So subtract the 60 from the 180 to get 120. Divided by 2 is 60. So check this out. This is a 60, 60, 60 triangle. So what's the name of a triangle that has all three angles 60 degrees?
Equilateral?
Exactly, that's equilateral. Okay, so it's an equilateral triangle, so that means that not only are all of the sides that come out of the middle equal to R, but this side over here is also equal to R, so they're all equal to R. So the perimeter, well, there's 6 sides, all length R, so that's why we get the 6 times R. And R is, or the diameter is 2R. So if we replace 2R with D, we get 3 times D. So on the one hand, we have for the circle, pi times D. And for the hexagon, you have 3 times D. So if we calculate the ratio of the perimeter of the hexagon to the circumference of the circle, the claim is we get the base 60 number, 5736. So let's actually calculate this out. So in other words, it's saying if you take this number divided by this number, you get the 5736. Okay, so let's actually calculate that out. So let's calculate this in base 10 to see what we get. So remember, if your number looks like this, so we don't have any integer part, the next one is divided by 60, and the next one is divided by 60 squared. That's because it's a base 60 fraction. And then going from base 60 to base 10, remember that's the easy calculation because we just plug it in and do the calculation. So our 57 over 60, it looks like there's a common factor of 3. So I'm going to factor the 3 out of the numerator and I get 19. I factor the 3 out of the denominator to get 20. And then I'm going to go ahead and say is, well, what is 60 squared? So 60 times 60 is 3600. Let's simplify further. So this is still 19 over 20, but this is 36 divided by 3600. I divide the numerator and denominator by 36 to get 1 over 100. Okay, so looks like I want a common denominator of 100. So I'm going to multiply this numerator and denominator by 5. So 19 times 5 is 95, 20 times 5 is 100, So now I get 95 over 100 plus 1 over 100 is 96 over 100. There's a common factor of 4 in the numerator and denominator. So divide that out. So 96 divided by 4 is 24. 100 divided by 4 is 25. So I get the fraction 24 over 25. So in modern terms, we would say that the perimeter, my stylus randomly changes to erase from time to time. So just a quirk. Okay, so the perimeter of the hexagon divided by the circumference of the circle is this number. So in other words, that's what the tablet seems to be saying. So the 5736 becomes 24 divided by 25. And then remember that the formula for the perimeter was 3d. The formula for the circumference was pi d. There's a common factor of d in the numerator and denominator. I'm going to divide that out. So that means that the perimeter divided by the circumference, which is 24 over 25, is equal to 3 divided by pi. Now we can calculate what is the value of pi that we get by using that number is 3 over pi. So I prefer to have the pi in the numerator, so I'm going to just flip both of my fractions. So pi over 3 is 25 over 24. And so therefore, I'm going to take this equation here, multiply both sides by 3 to get pi by itself. So it's 3 times 25 over 24. And so notice that the 3 in the numerator cancels out with the denominator's 3 times 8. So that simplifies to 25 over 8. And so that's 3 and an eighth, or 3.125. So that would mean that according to the Babylonians, the so-called circumference pi is 3.125, which is a better estimate than just 3.0, since we know now that the correct ratio is 3.14. And so the 3.125 is going to be closer to the actual value. And then again, in Egypt, they had 3.16, which was also a pretty good estimate, but that was the area pi. So we cannot say that one or the other had a better value of pi because they were doing different calculations. One is the ratio of the area to r squared, the other is the ratio of the circumference to the diameter. Now, last time we talked about, number one, how to convert base 60 integers into base 10 integers. So we know how to do that. That's by far the easiest calculation. Then we learned how to convert base 10 integers into base 60 integers. So that's a little bit harder. And then we also learned how to convert base 60 fractions into base 10 fractions. But by the way, that's what we just did in the example above, because remember, we were given a base 60 fraction. we converted into base 10 by just saying that the first digit is divided by 60 and the second digit is divided by 60 squared. And if you had more digits, you divide by 60 cubed, 60 to the fourth, etc. And then you just, simplify, you'll get a decimal, or you could write it as a fraction. But the point is that again is not too hard to do as long as you understand that these represent numerators and the denominators are powers of 60. So now the harder question is, how would you convert base 10 fractions or decimals, either way you want to look at it, into base 60? You'll see when we look at the method that the method works pretty much the same way, regardless of whether your base 10 number is written as a decimal or as a fraction. So what I'm going to do is I'm going to work through an example. So for my example, I'm going to convert this number, which has an integer part as well as a fractional part, meaning the decimal part. I'm going to convert that into base 60. So we're going to do it in two parts. Part one is, let's do the integer part. So we learned how to do that last time. But the bottom line is that 80 is a pretty simple number to work with because 80 is 1 times 60 plus 20 times 1. Remember, these are both powers of 60. This is 60 to the 0, and this is 60 to the 1. So if you've forgotten how to do this, I will be posting the notes that includes the examples that we did in class on Tuesday. So you'll have that to refer to. Okay, so whatever number multiplies the 60, that's one of our digits. That's our first digit. And the number that's multiplying the 1 is our second digit. So that's where we got those two. So that's going to be 80. So the integer 80 is written in base 60 as 1, 20. Now I want to do the fractional part. So I'm going to start working on the fractional part just by appealing to the definition of what do we mean by a base 60 number, or in particular, a base 60 fraction. I'm going to appeal to the definition to start the problem. But as I start doing the steps, I'm going to notice a pattern that's going to make it easy to finish. And then when you do an example yourself, you can do the shortcut that we're going to learn at the end. So here's what I'm trying to do. I'm trying to write 0.1027 as a base 60 fraction, or you could think of it as a base 60 decimal, but decimal actually contains the Latin word for 10. So, I mean, technically it's not a decimal, but it's the equivalent of a decimal. So we're trying to figure out if I'm going to write this 0.1027 as base 60, it's going to be some numerator divided by 60 plus some numerator divided by 60 squared plus some numerator divided by 60 cubed, plus I don't know how many I need to do. And so just like in base 10, decimals can potentially go on forever, that can happen in base 60 as well. So then the other thing to keep in mind is, because of the fact that these are base 60 digits that I'm looking for, the X, Y, Z, and whatever else, these are going to be base 60 digits, which means integers from 0 to 59. So X, Y, and Z, and whatever else are going to be integers between 0 and 59. So what I'm going to do is I'm going to start by trying to calculate the X. So the X is going to be the numerator when the denominator is 60. So to begin with, I'm just going to say, well, I want something divided by 60 to be equal to 0.1027. What is that something? So first of all, I'm going to write my 0.1027 as a fraction, and I'll just work with the fractions. This is why if you started with a base 10 fraction, you follow the same steps, except that you don't have to do the first step where you do this conversion. You just work directly with the fraction. So what I want is that, so right now I'm just kind of ignoring all this because I'm trying to find X. So can I find an X so that X over 60 is equal to 1027 divided by 10,000? Well, solve for X. So I'm going to multiply both sides of this by 60 in order to solve for X. And so notice I get, well, here's the result. It's going to be 61,620 divided by 10,000. So it's 6, because if we just ignore this, that's 60,000 divided by 10,000. So it's going to be the whole number 6 plus the fraction 1620 divided by 10,000. Now, by the way, this fraction over here can be simplified. So I'm just going to divide the numerator denominator by 10. So I get 6 and 162 divided by 1,000. Now, I'm going to plug that in and see what this means. So here's what we have so far. 0.1027 is equal to the number I calculated for X in the numerator and then 60 in the denominator. Well, that numerator is terrible. Well, so I'm going to separate this out into two pieces, because remember, this represents a plus. So I'm going to separate it out into two fractions. 6 over 60, well, that looks kind of nice. I like that part. But the rest of it I don't like. It's a fraction divided by 60. So basically what I'm going to do is I'm going to say, well, let's let X be 6 and then use the rest of this to figure out what comes next. So right now this calculation looks kind of messy, but we'll see why it simplifies after we do the next step. So the numerator that we're looking for is x equals 6. We don't want a fractional part. We're looking for integers. And then we use the fractional part to figure out what the next numerator is. So remember, we're trying to figure out a numerator divided by 60 plus a numerator divided by 60 squared plus a numerator divided by 60 cubed plus who knows how many additional steps. So now we want to figure out, what does the numerator y have to be if the denominator is 60 squared? Okay, so this looks a bit messy, but we have the numerator that we're looking for, y, divided by 60 squared is equal to this messy part here. I'll show you why I didn't bother simplifying it. So I'm going to multiply both sides by 60 squared. So that leaves the y by itself. And then I multiply this ugly looking fraction by 60 squared. And notice that one of the 60s cancel out with this. So in other words, it's really just 60 times that fraction. So the fractional remainder that we got when calculating x, all we did is multiplied that number by 60. So let's go ahead and multiply that out. The numerator is 9,720, which is 9 plus this fraction. The fraction has a common factor of 10 in the numerator and denominator. I'm going to get rid of that to make my fraction simpler. So that's now 72 over 100. So 9 plus 72 over 100. So we're going to take y equal to 9. And then we're going to use that fraction that's left over to figure out what the next digit is. Okay, so here's where the shortcut comes in. The previous two steps have something in common. What we did was we multiplied the number that we had left over from the previous step, or if it was just a fraction, it was the number we started with. We took that number and we multiplied by 60. We kept the integer part as our digit. And then use the remaining fraction to find the next digit. And how did we find the next digit? We multiplied by 60, keep the integer part, and then use the fraction to find the next one. So since we did that for our first two steps, to make life easy, I'm just going to use this shortcut to find the remaining digits. So to find the next digit, what I'm going to do is I'm going to take the fractional part, which was 72 over 100. I multiply it by 60. I carry out the multiplication. I write it as an integer plus a fraction. I'll simplify the fraction. I keep the integer part to use as my digit, and I use the fraction part to find the next digit. So I'm going to take the fraction from the previous step, multiply by 60 to get the next digit. And notice that there's no more fraction. That means we're done. So our answer is going to be, so let's just remind ourselves what we've done. The integer part was 120. X was 6. Y was 9, just the integer part. And then the next two digits are going to be 43 and 12. So our final answer is the integer part. And remember that in our modern notation, we separate the digits with commas. And then we separate the integer part from the fraction part using a semicolon. And so then these were the digits that we just calculated. And then we can check by converting it back into base 10. So 1 times 60 plus 20 plus 6 over 60 plus 9 over 60 squared plus 43 over 60 cubed plus 12 over 60 to the 4th. Plug that into your calculator and you get the original number we started with. Now, if it turned out that the number was not a terminating decimal, which can happen in base 60, just like in base 10, what you would have to do is just stop at some point. Maybe the question would be like, what are the first 3 decimal digits of this number? And then when you did your check, because you didn't do all of the digits, you only did some of them, you'd get an answer that would be close to what you started with, but not exactly. Like it would be off in some, decimal digits at the end. Okay, so I'm going to be giving you a new homework assignment, and it's going to include reading from the textbook Math Through the Ages. And I did want to remind you that that's available as an ebook in the library for reserve. So if you wanted to read from the library version, you can. I believe that the checkout time is maybe 3 hours, just so that everybody has a chance to look at it who wants to. So anyway, so I will be giving you a reading assignment from that book, and it'll be a pretty short reading assignment. Probably a couple of problems from that book, plus a couple of problems that are specific to the Babylonian number system and the base 60 number system. So the current assignment with the pyramids is not due until Saturday. And then either tonight or tomorrow, I'll post the next assignment that will include the Babylonian number system. So now that we know a lot more about Babylonian numbers, and we also know a little bit about how the Babylonians viewed pi, meaning the ratio of the circumference to the diameter, let's see what else they did. Like, what other kind of mathematics do we see on the Babylonian texts? So there are problem texts and there are table texts. Now, the problem texts probably serve the same purpose as the Egyptian problem texts, namely as an educational tool, kind of like a textbook to teach other scribes how to solve these problems. But the problems themselves often were real world problems that scribes needed to work on. And so if you look at these two texts, this one here looks like geometry problems. So for example, you can see squares with lines written in them. Here's a square with a circle inside of it. Here's a square with some diagonals. So you can imagine that they're probably going to be doing things like calculating the lengths of diagonals and that sort of thing. In this text on the right, what you see are a lot more maybe words and numbers. There is a drawing over here of a circle, but you see mostly words and numbers, not so much drawings. So these are examples of problem texts. But we also have table texts. So let me just tell you a little bit about why. So think about when you were in elementary school and you learned how to multiply. The first thing that you had to do is, after you learned what multiplication meant, you had to learn how to do some actual multiplications. So they started you out small with multiplying one-digit numbers by one-digit numbers. And then you probably had to actually learn the times table for 0 through 9. So you needed to know, what is 3 times 7, what is 5 times 4, etc. And then once you learned the times table, at least for 0 through 10, then you could use that. And then the algorithm that we have for multiplying, like say 2-digit numbers by 2-digit numbers, but you'd use the fact that you already knew what 5 times 4 was to help you to calculate, say 64, times 52. So you needed to know your times tables. The problem is in base 60, if you were going to do exactly the same thing, you would need a table that contained 0 through 59 across the top, and then 0 through 59 across the bottom. And then all of the possible values. So that table is way too big. That 60 by 60 times table that you would need to perform more complicated multiplications, that's way too big. As a result, they made times tables for individual numbers. So for example, this table is basically typed up, so it's a modern depiction of what was on an actual tablet. And this is a multiplication by 7 times table. So if you were doing a multiplication that required multiplication by 7, you'd use this. Over here, we see a times 9 multiplication table. But it turns out that they didn't also have to make a multiplication by 34 times table, because they knew that to multiply a number by 34, you multiply by 30, you multiply by 4, and then you add the results together. So remember that even though they're using a base 60 number system, their digits are written in base 10. So basically, what this amounts to saying is they knew the distributive law and they made use of that so that they didn't have to make times tables for numbers that were bigger than 10. So you have separate tables. For example, multiplication by 7 is its own table. Multiplication by 9 is its own table. And the full table would have, 9 times 1, 9 times 2, ... 9 times 59, theoretically. Okay, so here's an example. How would you multiply 34 times 9? Well, you'd multiply the 4 times 9. And if we look over here on this table, this circled in green or highlighted in green is 4. And then you look on the other side, and that's 36. So this is 3 10s and 6 1s. Next, what's 30 times 9? Because 34 is 4 plus 30. So look up 30 times 9. So here's 30. And 30 times 9. And the answer is going to be right there. And it's 430. Remember, it's written in base 60. So 30 times 9 is 4. So here's the 4 right here, followed by a 30. And so now what we're going to do is we're going to add and. So we get 4, 66. By the way, you had to know from context what this 36 meant. Does it go in the ones column or the tens column, or rather the 60s column, in order to add? In any case, this goes in the ones column, the 30s in the ones column. You add them and you get 66, and then you have a 4 plus nothing in the 60s column. So you get 466. But the problem is the digits have to be 0 through 59. So just like in base 10, if you added up the rightmost column and you got 13, you'd write down the 3 and you'd carry the 1, because 13 is 10 plus 1, and you'd move that, 10 plus 3, you'd keep the 3 in the ones column, and then your 10 becomes a 1 in the tens column. Works the same way. So this consists of a 60 plus a 6. So this 160 has to go into the 60s column. So you carry the 1 to get 5. So works exactly the same way with carrying, except that what you're carrying is the 60s, whereas in base 10, you're carrying the 10s. Okay, so any questions about this? Finally, here's one more kind of table text. Inverses. So this goes back to the earlier question of, did they understand inverses, and that inverse when you multiply by the original number is 1. So this is evidence that they actually did understand the whole concept. And so here's the idea behind the table of inverses. They did not want to perform divisions. They only wanted to perform multiplications. So they asked the following question. dividing by x corresponds to multiplying by what? So let's first look at an example in base 10, and then we'll see what that means in base 60. So in base 10, there's actually a trick for dividing by 5. And I bet some of you have figured out this trick. So if I need to divide by 5 in my head, I multiply by 2 and move the decimal. Why? So dividing by 5 is the same as multiplying by 1/5, and 1/5 is 2/10. So that's why I will multiply by 2, and then when I'm done, I need to move the decimal because I have to divide by 10. So basically, according to the Babylonians, therefore, the reciprocal of 5 would be 2. If they were working in base 10, they would say the reciprocal of 5 is 2, because in order to divide by 5, you have to multiply by 2 and move the decimal. So that's exactly what they're doing, except that now the denominator isn't 10, it's 60. So in base 60, for example, if I wanted to divide by 4, so whatever number I have, I'm trying to divide by 4, that means I'm multiplying by 1/4. And then I ask, well, what would my 1/4 be if it was a fraction that had a 60 in the denominator? Well, the numerator would be 15. So in base 60, in order to divide by 4, I first multiply by 15, and then I move the decimal. And so that's highlighted here. The reciprocal of 4 is semicolon 15. So it's not 15 as a whole number, but it's the fraction 15 over 60. And so that's why we say the reciprocal of 4 is 15. And so basically that's what it actually says on this text. So there are some words, but here's the 4, and then here is the 15. So the bottom line is dividing by 4 is the same as multiplying by the base 60 number 0, 15. Okay, so that's it for the numbers. And what I'd like to do is at least start on Babylonian algebra. So now we're going to look at what kind of problems did we see on the problem text. And by the way, all of these tables, both the multiplication table and the inverse tables, are things that they would have had handy to actually solve these problems. So, in other words, before you can solve an algebra problem, you need to know arithmetic. And so then they had these table texts that helped them with the arithmetic, and then they did the algebra. Okay, so when I say Babylonian algebra, I put the word algebra in quotes because on the one hand, the problems that they're solving are problems that are just like problems that you solved in high school algebra. So they're very much algebra problems in that sense. So you probably solved exactly the same kind of problems in high school algebra. But the Babylonians solved the problems without using any algebraic notation. And so as a result, what they did on their texts is basically showed what steps you had to take using words and doing the calculations, but without ever using any sort of algebraic notation. All right, I think I'm going to skip this next slide, might come back to it in next class. Okay, so here's an example of Babylonian algebra. So let's call this sample problem 1. I have 2 numbers. The sum of the numbers is 32, and the product of the numbers is 231. What are the 2 numbers? Now, in high school algebra, we would say, okay, I have 2 numbers. I'm going to call them x and y. And then I'm going to say x plus y is 32, and then x times y is 231. And I'm going to solve for x and y. So that's what I would have done in high school algebra. But what did the Babylonians do? Well, the first thing they did was they found the average of the 2 numbers. In other words, remember that the sum of 2 numbers, x and y, is x plus y divided by 2. So it's x plus y divided by 2. So that's the mean or average of the 2 numbers. So it's the sum divided by 2. That's their first calculation. Next, whatever number you got from that step, square it. So 16 squared is 256. Next, take that number and subtract the product. So remember that the product is 231. So you take the number from the previous step, subtract the product. So 256 minus 231 is 25. Then whatever number you got there, take the square root. So I take my 25, I take the square root of that number. By the way, they did not have that square root notation. They just took the square root. And they actually knew how to take square roots, even when the numbers were, complicated. So here, the square root is easy because it's a perfect square. But if it was the square root of 24 instead, they could have handled it. Now, it turns out that this number that you get in this step, take the square root of the number from the previous step. What that gives you is, if you think about your 2 solutions, x and y, it's how far those numbers are from the average value. So that means that one of your answers is the average plus the deviation. The other one is the average minus the deviation. And so your 2 numbers are 21 and 11. You can check 21 plus 11 is 32. 21 times 11 is 231. So that means I have correctly found the answer. So basically what you would see in the text is, take the sum divided by 2, square that number, subtract the product, take the square root, and then add and subtract. So that's how they would solve that particular algebraic problem. Let's look at another one. Sample problem 2. So the previous problem was the sum and product. This one is difference and product. So I have two numbers. The difference between the two numbers is 24, and the product is 145. So what are the two numbers? Here's what they would do. Now, notice that these steps kind of look like the steps in the previous example, except they're done in a different order. So, notice that basically almost our last step is calculating the deviation, whereas here, the first step is calculating the deviation. So basically, it's the same steps, but in a different order. So you start with the deviation from the mean. So I'll be drawing an illustration of what all of this means, but if you think about it, I have two numbers. The average is the number that's halfway between them. And so the deviation from the average is going to be the difference divided by 2. So right now I'm focusing mostly on what they did, and we'll look at the more modern interpretation in a minute. So you take the difference, divide by 2, get 12. Next, take that number and square it. Next, you add the product. So the number from that step plus the product, which is 145, you get 289. Now you take the square root. Okay, so that was 17. And then once again, so just like in the last step, it was going to be the average plus the deviation and the average minus the deviation. That's going to give you your two answers. And then you check. The difference needs to be 24, so 29 minus 5 is 24. When you multiply them together, should be 145, it is. So it looks like I solved this problem correctly. But now what I want to do is I want to look at this from the perspective of a modern person. So that means that I'm allowed to use algebraic notation, and that's going to make my life easier, and it's going to help me to understand, why do these steps work? So I have two numbers, x and y, and I'm going to make x the bigger of the two numbers. I'm going to call the sum 32, so that's x plus y. And I'm going to use the letter A to represent the product, because I'm going to think of the product as being the area of the rectangle that I just drew. So then what were the steps? Find the average. So I'm going to call the average alpha. it's the sum divided by 2. And in our example, that was going to be 16. So because the sum is 32, find the average squared, subtract the product. So alpha squared minus capital A. The deviation from the average is the square root of that. So it's a square root of alpha squared minus A. And alpha squared minus A was 25, so it's 5. And then the larger of the two numbers was the average plus the deviation from the mean. The smaller of the two numbers is the average minus the deviation from the mean. And so that's basically giving it a more algebraic view. I could do the same for problem 2. So let me just, I inserted a picture here because we're assuming that X is the larger of the two numbers, Y is the smaller of the two numbers. The mean is what we're calling alpha. And so then X minus Y, remember X is the bigger number. So the distance from Y to X is X minus Y. And then the average value is the point that's right in the middle. And so the distance from X to the point in the middle, or the distance from Y to the point in the middle, is just half of the total distance. In other words, it's X minus Y over 2. Then the next step was to square that number. Then add the product to it. And then the square root of that number is the average, so the square root of delta squared plus A. And then we did the average plus the deviation from the mean is 25. The average minus the deviation from the mean is 5. And so that's how we got our 2 answers. So algebraically, that's what the calculations actually look like. So notice that in both of these, there's a formula that compares the average, the deviation from the mean, and the area. So there are 2 different formulas. This one, alpha, is the number that you've solved for. This one, delta, is the number that you solve for. So what I want to do is look at those 2 formulas. So from problem 1, we had delta is the square root of alpha squared minus A. If you square both sides, you get delta squared is alpha squared minus A. And then if you add A to both sides, you're going to get alpha squared is delta squared plus the area. From problem 2, we had alpha is the square root of delta squared plus the area. Square both sides and you get alpha squared is delta squared plus A. And notice that it's exactly the same formula. So the bottom line is that this is going to be a key formula in understanding their method. And so the question is, can we justify this formula? And this is just reminding us what the two numbers mean. Alpha is the average or the mean, which is just x plus y over 2. So it's the sum divided by 2. And the deviation from the mean is x minus y over 2. So x is the bigger number. Delta is the distance from x to the mean. It's also the distance from y to the mean. And then the mean is the midpoint of x and y. So let's prove using modern methods that with this definition, that alpha squared is equal to delta squared plus a. Where we're assuming that the two numbers are x and y, x is greater than y, s is equal to x plus y, a is equal to x times y, alpha is the average of the two numbers, and delta is the deviation from the mean, which is x minus y over 2. So just everything that we've seen before. And so here's the algebra. Usually when I'm proving an algebraic formula or that sort of thing, I usually start with the more complicated side and then try to simplify it to get to the simpler side. And that method works well here. So basically, I'm just going to take this. I'm going to plug in everything. So delta squared. So delta is x minus y over 2. Square it. The area is x times y. Now I'm going to just expand that out. So x minus y squared is x squared minus 2xy plus y squared. And then the 2 squared is 4. And then I still have the plus xy. Let's put everything over a common denominator. So my common denominator will be 4. So this becomes 4xy over 4. Now I can combine these into one fraction. So here I had a minus 2xy over 4 plus 4xy becomes a plus 2xy. But notice that this numerator is now just x plus y squared. The denominator is 2 squared. So this simplifies to x plus y over 2 squared, which is just alpha squared. Now, to be clear, the Babylonians did not have algebra. And so we know that this is not how they justified this. They had a completely different way of doing it. And basically, it was a proof by picture, so using geometry. So next time we're going to look at that. We're going to look at the Babylonian method for justifying this formula. And then we're going to wrap up the Babylonian algebra. Okay. Oh, okay. So before we wrap up, I see a very, very interesting question in the chat. So I assume that you were talking about the reciprocals for numbers that weren't divisible by 60. So first of all, let me begin by saying, why did the Babylonians use base 60? Probably because it has a lot of divisors. So a lot of numbers, it was very easy to figure out the reciprocals because 60 has a lot of divisors. But what about numbers that weren't so simple, like 7? Well, the problem is that they couldn't do that so simply. So it was actually more complicated. And so typically when you see these inverse tables, they exclude the numbers that you don't have an easy reciprocal for. The only other possibility would be that they would understand that their decimal would go on forever and that whatever answer they got would only be approximate. And so that's the reality. So just like when you're dividing by 7 in base 10, you know that it's just going, unless the number is evenly divided by 7, then your decimal is going to go on forever. And then the same thing would have happened dividing by 7 in base 60. So it wasn't a simple answer like it was with 4, for example. So yeah. So yeah, thank you. That was really an excellent question. And they would have had trouble finding the reciprocal in an easy way, so they would have done it in a, a harder way. Okay, so any other questions before we wrap up? Okay, so don't forget, homework is due on Saturday, and look for your next assignment either tonight or tomorrow, and that'll be due next week. All right, see you guys in class next week. Bye.